To continue the discussion of topics about reactions of ionic compounds in solution, we need to talk about typical kinds of chemical reactions, specifically three particular ones: precipitation reactions, and acid-base neutralization reactions, and oxidation-reduction reactions. I'm going to give you a very short discussion of those three types of reactions on this recording. Now, this topic, our heading for this section, sounds kind of silly. Some ways that chemical reactions occur. These are not an exhaustive set of descriptions of chemical reaction processes, but there's some common ones that we need to be able to work with and to be able to recognize. There certainly are others, but let's work with these for reactions in aqueous solutions. These are relatively common examples. The first type that we need to know about is called precipitation reactions. These are processes in which you take two soluble ionic reactants. Notice they need to be ionic, and they need to yield an insoluble product. And that is going to typically literally fall out of solution, as is suggested in the photograph here. The photograph shows a mixing of the two compounds in the reaction shown. So you have lead nitrate, lead-2 nitrate, combining with potassium iodide, and these are both soluble, noted by this AQ designation. And when you mix them together, you end up with a product that comes out of solution. Well, how that happens is because you have to think about the ions that these compounds contain. The lead-2 in this case is +2, the nitrates -1, the potassium's +1, iodide's -1. And what that happens, and you have these dissolved in water, the soluble ionic reactants mean they totally dissociate nicely in water and in water, and are totally surrounded by water. But that means that there's a possibility of their rearranging and combining to create an insoluble product. So the insoluble product here turns out to be the lead with iodide. Lead-2 iodide is its technical name. The remaining ions in the solution are the potassium and the nitrate ions, which you can consider as a second product, but in fact they are still also aqueous and dissociated in water. So the lead iodide is no longer soluble, not surrounded by water, and literally falls out to the bottom of the solution. Now, in this particular example, it's a nice, pretty yellow color. Oftentimes, your solution is going to be cloudy. It may or may not be really obvious like that. And the precipitate will settle out with time. Settles with a little bit of time. So anything that goes cloudy or makes something obvious that's more opaque is a good clue that you've got a precipitate. These kind of reactions are going to be resulting from swapping partners, swapping cation and anion pairs. And so as noted from this example, you would look at the charges of the anions and cations and recognize that you're going to put a new cation and anion together in the products. And we will describe later how you know which ones are going to be soluble or not. Notice they're both ionic compounds, but this one turns out to be very soluble, and the other one is very insoluble. Lead is commonly an insoluble compounds, but you don't know that until we find the rules. Okay, that's reaction category number 1. The next reaction category is, follows after this one. So if you're not part of the solution, this is a chemistry joke, guys, you're part of the precipitate. So if you, in the precipitate, you're at the bottom of the beaker, the bottom of the test tube. If you're part of the solution, it's floating around in the solution. I know, silly chemistry jokes. The second reaction category that you need to see is, and be familiar with, is acid-base neutralization reaction. So an acid reacts with a base to neutralize, so that what results is neither acid nor base. And the hallmark for those reactions is that water is going to be a product, and oftentimes a salt. It's not foolproof, but oftentimes there will be a salt. The salt results from the remaining portions of the compounds in your reactants that do not make water. So in this example with hydrochloric acid and sodium hydroxide, will have to, you can think of these in terms of cation and anion pairs swapping again. So think of that. Think of cation and anion pairs changing. And let's see, I'll write the words in there. Oops, swapping. Uh-oh, I have to get rid of that extra mark for you. I don't care for that. So cation and anion pair swapping. First of all, you'll have to know when things are acids or bases. We'll come to that discussion a little bit later in the chapter. But you're going to think in terms of a cation and anion pair swapping. And when you do that, you can imagine that the hydrogen ion combines with the hydroxide ion, and the chloride ion will combine with the sodium ion. And that gives you our salt. In this case, the salt is ordinary sodium chloride, but any anion-cation pair is going to be a salt. Now, I've overstated something just a little bit here. I should clarify. The HCl is actually a molecular compound. Aha! It is a molecular compound because it is a pair of nonmetals, but it is an unusual one in the sense that it will dissociate to make ions in water because it is a strong acid, and therefore you get complete dissociation in water to make ions. So complete dissociation to make ions in water. So it is a molecular compound. It is not truly ionic. Sodium hydroxide is definitely ionic, no problems there. But HCl is a pair of nonmetals, and that does not fit our definition for ionic compounds. So it's kind of an odd one there, but molecular compounds such as acids can produce ions in solution, specifically strong acids for sure. So water then is produced by the combination of hydrogen and hydroxide, and so only when you have hydroxide ions present can you make water in the product, but that's common. So acid plus base makes a water and a salt, and that's one thing to think about. That's a good generalization. All right, the third reaction type then is going to be yet new, and it will be a little more less uniform, I guess is a way of saying it. The oxidation and reduction reactions, we call them by a nickname called redox. We say oxidation and reduction, yet we nickname it in reverse order. And these are reactions in which one or more electrons are going to be transferred from one reaction partner to another. And so electrons passing back and forth constitute redox reactions. Now, how do you know and how do you recognize them when you find them? They're going to have certain things that are more obvious. First of all, there's no need to have aqueous ions in these reactions. For example, you have a solid here, and there's something else that's aqueous, and that's what's represented in the photograph at the right. That would be some magnesium ribbon reacting with hydrochloric acid, and one of the products in this case turns out to be hydrogen gas. So the bubbles are the gas. And so that's very characteristic of this type of reaction of an acid with a metal. Now, how do we know that electrons are being transferred? Well, here you have magnesium as a solid. It's just magnesium metal. It's what that strip in that picture looks like. But then you end up with magnesium ions, and they're +2, they're cations. And so now the magnesium has gone from a neutral atom to a cation. And so it had to, the cation is formed because the metal had to lose some electrons. Loses 2 electrons for each magnesium atom. Where do the electrons come from? Well, you have to think in terms of cations and anions again. We'll do more examples, but I just want to give you the first basic notion with these here. Think in terms of HCl having the potential for ions. When you put it in water, it contains hydrogen ions. It will produce hydrogen ions and chloride ions. And the hydrogen ions are positive and the chloride ions are negative. Well, where are those electrons going to go? Apparently, you form hydrogen gas. So hydrogen gas is neutral hydrogen. It neither has a cation or anion characteristic. And so if the hydrogen cations gain electrons, then you can turn it into neutral hydrogen. So this is an elemental form of hydrogen, is another way of saying it. And so there, you can identify that oxidation reduction has taken place when an atom turns into an ion or vice versa. And so in this case, the hydrogen ion turns into a molecule, and the magnesium atom turns into an ion. So atoms and ions are good clues. Another clue is elements turning into compounds is a good clue that you have redox going on, because you start off with an element, such as magnesium, and you turn it into an ionic compound, for an example. Okay, that was a little more complicated than you might have first imagined, but we'll talk about these in a lot more examples later. But those are the three basic categories of reactions that we want to discuss in this chapter. As usual, I hope you find this helpful as you do your homework. I would hope you ask lots more questions as needed, and I'll see you in class.